Okay, I am, my throat is sore, but I am all hopped up on cough drops. So I'm going to try to do as many of these 2D kinematics practice problems as I can. Problem one, pardon the volume and if I'm breathing on the mic and all that stuff, but yeah, I'm sick. What can I say? So, problem one, we have here Santa Claus out delivering Christmas presents from New Orleans Reindeer, blah, 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 blah. Hanukkah Harry comes in to save him. So, three ways to do this problem. One, let's see if I can draw this here. Yes, I can. Okay. So we've got Hanukkah Harry, and we got Santa here. And Hanukkah Harry is going at 70 meters per second. Okay. Santa's going at 40 meters per second. And so Hanukkah Harry drops a bale of hay. Initially, the bale of hay has the same velocity as Harry, right? But then it starts falling, and it falls in sort of a parabola, and we'll have to do the math here. The height difference between them is 45 meters. So we have to figure out how long it takes to fall 45 meters. And so actually that's going to be common to all three methods. So maybe we can just go ahead and do that. So first we have to find out how long it takes the hay to fall 45 meters. Delta y is negative 45 meters. And we have, let's see, right, delta y is, just write the whole thing out, vy naught t plus 1/2 acceleration of y t squared. Well, obviously your initial velocity in y will be 0, and your acceleration in the y direction will be negative g. So what you get is that delta y, which is negative 45 meters, is 0 times t minus 1/2 gt squared. Oh, sorry, this is a squared. My bad. This formula needs a square there. Okay, so minus 1/2 gt squared. Really awesome people use 10 for g. I just wrote these problems using 10 for g, and it's a little easier. You can do more problems in your head or close to in your head. So negative 45 equals 1/2 times negative 10 times t squared. And what you get from that is that t squared equals, let's see, so divide the 10 through and then divide the 2, multiply the 2, and you get t squared equals 9. So the time it takes the packages to fall is 3 seconds. Now, this is where you get three different methods to solve the problem. One is to say, well, in 3 seconds, the package is going to fall 45 meters. So horizontally, delta x for the package, or the hay, is going to be the package's horizontal velocity, which is 70 meters per second, times 3 seconds. Okay, this is just equals vx times t, and that's going to go 210 meters. Okay, and then delta x for Santa, in the same amount of time, he's going to go 120 meters, because that's 40 times 3. Okay, that's a 3. Pretend that's a 3. Hey, I'm sick. What do you want? Okay, 120 meters. So Santa goes 120 meters, Harry goes 210 meters, and the package goes 210 horizontally. So the answer is that Harry should drop the package when he's 90 meters behind Santa. Okay, the other two ways to do it are with different choices of coordinate frames. So this is sort of using a coordinate frame that's attached to the ground, say, and Santa and Harry are zooming over. Okay, if you use a coordinate frame attached to Santa, I will draw that in green. Then what happens is Harry is there, Santa starts out there. Santa is motionless because this coordinate frame is attached to Santa. And so Harry is actually just going, relative to Santa, he's just going 30 meters per second. So then it's a question of, right, then all Harry has to do is sort of bomb this onto the quote-unquote stationary Santa. Okay, the third way, and the numbers end up being the same because it takes 3 seconds to fall. Harry's going 30 meters per second, and the package, the hay, is going to should reach Santa right when Harry goes overhead because they have the same horizontal velocity. So it's still 3 times 30 meters, 3 seconds times 30 meters per second, 90 meters. Okay. Third way to do it, which is really even easier, is to attach your coordinate frame to Harry. And so there's Harry. And so Santa now, in the Harry-centered coordinates, is not stationary. He's not moving to the right. He's actually moving to the left at 30 meters per second. And then Harry just has to bomb his hay straight down, and he just has to time it so that Santa walks right under him, or not walks, but flies right under him at the time the package arrives, which is 3 seconds after it's dropped. So 30 meters per second, you have to drop it when Santa is still 90 meters away. Simple enough. You get the same answer all three ways, and it's such a trivial problem, or an easy problem, that it doesn't really matter. But it's a nice illustration of how picking different coordinate frames can make the problem maybe look a little different, but it's really the same thing. All right, on to 2.